Okay. So the question asked, basically, we lost something overboard, and we want to go down and get it. We want to know if in regular gear, which we can only go about 100 meters max, can we get down that deep? How deep is it and whatnot? So to figure out how deep it is, we use a blowhorn. We send a signal, a sound wave, to the bottom, and it reflects back. Okay, we know that speed is distance over time, right? So we can treat distance as speed times time. But it's an echo, which means it went down and back, so that's twice the distance, right? So there's two ways you can do this. Either double the distance or half the time. It really makes no difference. So the distance equals v times t over 2. That's the depth in which it had to go down. Okay? So the speed is what? What's the speed going to be in this problem? Velocity of what?
Frequency.
Velocity or frequency?
Frequency.
Velocity, speed, okay, of what? Of what? Go on, so sound, okay?
Sound through water.
Yes, thank you. Okay, so it's going to be like 460 meters per second, something like that, and we'll calculate that in just a minute. Times, what is it, like half a second, did it say? Okay, so 0.5 seconds over 2. All right? So this will tell you what your distance down is. I don't have a calculator. Actually, the first page here. First page is what? See where it says speed of water right there? Can you read that to me? Okay, to determine the speed in water, right? The speed of water in water, right? That's the E over density to the 1/2. So your front page, so what is that? 10 to the 9 over 1,000, right? Because it's the density of water. Okay. This is given on your front page. I was going to skip driving it because it's given, but let's just do it anyways. So this is 10 to the 6, so it's 2.15 10 to the 6 square root. So give me this number first, and then we're going to do this number. Was this number equal? Anybody? Calculator. Okay, I guess I'm a calculator. This is the 9th, yeah, to the 9th power, yes. Oops. 1,466. 0.3 meters per second. Okay, so that's the speed of sound in water. So this is given to you on the front page. So I mean, the only thing I didn't do for you is write the equals 1,400, but you could have done the calculation yourself. So this is 1,466 goes here. So that means that 1,466 times 0.25. That means it is 366.6, 36.57 meters down. Now the deepest I can go with scuba gear is about 100 meters. Then I'm guessing that it's lost. What did I lose this time? So the phone is lost. So the answer is the phone is lost. Phone is lost because this is much deeper than I can go with normal scuba gear. Now, this problem was actually based on something that actually happened to me in the Atlantic when I lost my wedding ring when I got married in 2010. Took the boys on the scuba trip, and I actually was pulling my flipper off, and the boat pitched, and my ring went flying in the water, and I actually went down. It was only 100 feet, though. I went down and tried to find it.
Could you find it?
I did a grid and everything. There was a high current in that water, too, and I did a grid. I did like a 100-yard grid. Couldn't find it. The amberjack there weigh about 50, 60 pounds. I'm pretty sure one of them just snagged it up. You know? If you guys have ever seen amberjack, they're actually really playful fish.
What is that? Is that 36, 637?
366.37. Basically, it's a quarter of this, right? So think of 350 times 4. Okay. So the point is you have to figure out the speed of the water, you got to figure out the distance it went down, and then determine if you if you can reach it or not. Okay, that being said, back in the 80s I worked as a saturation diver for British Petroleum, and I've logged dives for days deeper than 1,200 feet. It sucked. You know, it wasn't even so much the fact of dealing with the pressure and the cold and exhaustion, because you get really tired very quickly trying to do anything in that depth. The problem was when you're decompressing after you're in a little tin can with 2 or 3 other guys, your bathroom is a little bucket, right? No one's taking showers, and you have to sit like that for a little over 3 days. You know, and you're breathing the same air you've been breathing for 3 days. It really sucks, man. I'm just telling you. You know? But it paid pretty well. Okay, any questions on that one? Did it ask for anything else in the question?
Why you give the pressure?
Pressure?
Yeah, assume the pressure is constant 101.
On the surface.
Why you keep that when it using that?
You could use the pressure on the surface to calculate. Do you remember when we did delta P equals rho GH? Remember that? So there's another way you could calculate the depth, but often I give you guys information in an exam that's not useful, and the easy way I show you how to do the problem. It may be necessary for another way to solve the problem.
How do you get the 2.15?
This is, I give this to you on the front page, right? That's the formula right there in the front.
What is the E?
E is a modulus. It's a bulk modulus for elasticity. So this is what you do for a solid or a liquid. You would use the bulk modulus, which is the representation of the springs between the molecules or atoms. And that represents how much it wants to deform based on the pressure, which is, in essence, the definition of the speed of sound.
That is for water.
Yes, that E is for water. You got different ones for actual sand or metal or
Steel.
yep, and the density would be different too. But if you're dealing with gas, you're better off using the KRT, right? Or the NRT, right? So if you're doing the gas, you want to do the, what is it, the KT? The one I give you, it's on that front page as well. The one I have. Okay, so it's all it asked for, right? Or did I miss something?
Where does the 15 degrees come into play?
As you change the temperature of water, this bulk modulus would actually change value. So the 2.15 times 10 to the 9 would change its value at different temperatures.
Also density will change, right?
The density will change, but the density of water doesn't change a lot. I mean, it's an incompressible fluid, so it doesn't change a lot. The only time you see a strong change in density is between 4 degrees and 0 degrees. Other than that, it's like 0.99 pretty much.
It's cold inside.
Okay, we're good? So that's number one. So that's a pretty easy problem, right? So basically, you just realize, force over distance, you find the speed of sound, plug it in, get your depth, and determine whether or not you can retrieve it. And what was number 2?
Two pulsars in the Crab Nebula are emitting gamma ray bursts regularly. One of them has a frequency of 1.675 times 10 to the 13 hertz. The beating between the two bursts is causing a local gravity anomaly at 45 hertz. What is the frequency of the other pulsar?
So these are the short answers. Man, I'm really going easy on you guys.
That I guess beat frequency would.
Yeah, okay, so in general, when you're having a beat frequency, that's two frequencies that coincide with each other, and literally, it's just some factor of their combination. So, like if I had frequency A plus frequency B, I'd have a beat at just adding those. That'd be F beat 1, right? And then I'd also have a beat at, twice it, or 3 times it, or 5 times it, and so on. You know what I'm saying? So any integer value of this combination is going to give me the beat frequency. So in that sense, if my first frequency is F1, so if F1, right, plus F2, okay, or plus or minus, because you can also do the difference, right, is equal to this guy of 45 hertz. So in reality, it could be, of the two, this could be 45 above the other one or 45 below the other one. Does that make sense? So so that your F2 here is going to be the 1.675 times 10 to the 13 plus or minus 45 hertz. The reason it's plus or minus is because you don't know if this guy is above it or below it by 45 hertz. Okay, Brent, it doesn't make sense?
Well, I was writing when you started talking about this.
Oh, okay. Okay, so in essence, you can think of the two waves interacting with each other, and every time that their frequencies line up, right, you're going to have like a resonance. So that happens, basically, if it's happening at 45 hertz, that means every 45 hertz the two sort of line up. So that means their difference is about 45 hertz. So what we're saying is, whatever this other frequency, the other Crab Nebula's frequency is going to be this plus or minus the 45, because it's either bigger or smaller by 45. Okay? I'll probably ask for some sort of explanation, but in general, that's what you're doing. You're looking for the comparison of these two beats so that their common frequency happens very often. Common is the wrong word. The combination of their frequencies happens every so often. Okay?
So that's all that we have to put for what the
I said I may ask for an explanation in words, but
and then it said ask if would humans be able to hear it or feel it?
Yeah.
So yes.
No. Well, you have to say more than that. So basically, humans can hear between 20 hertz, right, and 20,000 hertz. This is the frequency range of human hearing. Okay? So this is A. Okay? And B is, if this is the frequency range, yes, well, 45 is in this range, so B, yes. Because human hearing is within this range.
So we're talking about the
45.
Okay.
I mean, you don't really want to be talking about a human listening to gamma ray bursts. It's a bad idea. I don't know if you guys realize this or not, but if a gamma ray burst hit the planet, even if it was from like another galaxy, it would vaporize the atmosphere and fry everything on the planet. They're bad news. And they happen all the time. It's just the probability of it hitting us is pretty small. Hopefully it's pretty close to zero. Okay? Was that it? So bro was so busy writing, he forgot that part of the question. The part with the hearing. I know you are.
Okay, good. So the answer is yes because it's in the range of the human hearing.
Yes, because this is here. 45, right? Now if I said it's 45 kilohertz, then no, right? Because this is 20 kilohertz, so you're outside the range, right? Or if it's 5 hertz, then you're outside the range, right? short answer number 3. So you're gonna think about me every time you chew on that ice now, huh? Is that what's gonna happen?
I'm sorry, what?
I said you're gonna think about me every time you chew on your ice now. Is this still recording? Because this like screen went dark. It's like dark right now.
Can you touch it?
I just did. Nothing happened. I think it powered down. How long do you have it set for when it's not connected to power?
2 hours.
So, I mean, if it's not connected to power, running on battery, it'll go to sleep after 2 hours? Huh? No, I don't mean how long the battery will last. What I mean is there's hibernation settings that if you leave it alone for more than a few minutes, it'll just stop, or you'll either go to sleep or it'll log out, or depending on how you have it set. So it has a login screen now, so I don't know if it's in or not. Okay,
You want me to check?
it's your video. I don't know. It's your call. I mean, you can spend the next hour going over the question and find out you have nothing recorded. That would be sort of funny.
It wouldn't be funny.
It'd actually be funny. Tragic, but it'd be funny. Okay, so short answer number 3 is which one?
It is. Being recorded for 16 minutes.
16, good. Excellent. Excellent. You don't need me, you need the board, right? Well, someone has to tell me what the question is.
An astronaut on the moon attaches a small brass ball to a 1-meter string and makes a simple pendulum. She measures 15 complete swings in 75 seconds. Calculate the acceleration due to gravity on the moon from this result. Compare this value to the value calculated using Newton's universal gravitational law, and argue the same.
Okay, so what was the frequency that he saw the pendulum? He said how many oscillations and how long?
15 and 75 seconds.
Okay, so 15 oscillations in 75 seconds is what number of hertz he saw, right? And you guys remember the definition of frequency for a pendulum was 1 over 2 pi to the square root of g over L, right? And the L is 1 meter?
1 meter.
Okay, so that means we solve this for g, so we're going to have 2 pi f equals the square root of g over L, right? And then we square both sides, so we have 2 pi f squared times L equals g, right? So that's going to be 2 pi times 15 over 75 squared times 1 meter. Okay, that's going to give me the acceleration of gravity experimental, okay, based on the oscillations of the pendulum. So this would give me answer A, whatever G ends up being, G experimental. Okay, whatever you guys do in calculus. Now the second part says, well, okay, well compare that to Newton's universal law of gravity. I'll let you guys finish writing because I hear the pens going tick, 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 tick.
Do you hear me sitting here going, oh my goodness, where are we? Oh my goodness.
What does that say? Right. 2 pi, is that 15? I guess that's 15.
It's 15 over 75, right? You want to just move closer? Then the seat's closer, Brent. And there's closer
No,
seats.
I can see it perfectly like that. It's just
Yeah, I scribble, I know.
yeah. You should be a doctor. That would have been.
Actually, I've been told that many times. No. I mean, you know, when I finished graduate school, I was offered medical school in Miami. There's a program NASA has for any math, engineering, or physics, including chemistry, PhDs. They can actually go to Miami in 2.5 years to get an MD.
Yeah.
But I had been a graduate student for like 7.5 years, and you know, my kids were getting bigger. I was like, I need to get some money because graduate school doesn't pay much.
Seems like you need to learn a lot about the body before.
No, 2.5 years. It's an accelerated program, and when you graduate, you're a mission specialist for NASA. Done. It's one of those opportunities that I sort of regret in a sense, but don't at the same time. What? Okay, so did anybody calculate this? 3 over 25. No one? No, but you're reading. You can't be expected to read and to do the calculation and write and then absorb anything.
He's awake.
He's He's awake. What you saying? Like that's different from everybody else? Oh. So, awesome. Did anybody calculate it?
I got 1.579.
1.579. Horrible.
That's not right.
0.579 meters per second squared. Okay, so that's the experimental value you guys got. Now, according to Newton, right, the force of gravity from the universal gravitational constant is mass of an object times mass, in this case, mass of the moon, right, times g over the radius of the moon squared. Okay? Now, that means that the acceleration of gravity on the moon is going to be equal to this guy right here, right? Because remember, mg, m times little g, right? Yeah? That means that g in the theoretical is going to be the mass of the moon times g over our moon squared. You guys remember this? We did this a couple of tests back, kind of, sort of. Okay, so that means g theoretical. It's going to be, the mass of the moon is given, right? Maybe? What is it?
Mass of the moon is 7.34767309 times 10 to the 23rd.
What's the radius of the moon?
1738.1
1738.1.
kilometers.
0.1 kilometers.
Correct.
Okay. Okay, so this is going to give us what? This is 6. That's 17. Okay. 10 to the 6. So actually I can do this 1, 2, 3. Make that 10 to the 6, 10 to the 12, so 25. I don't know. You guys, whatever you guys come up with the calculator. Anybody? No one just wants to give me the answer, or what? I think I'm gonna have to make this a little harder.
Please don't. No, you don't.
If I can't, not everyone in the class can get an A. That's not right. I have to have some distribution.
What are you talking about? I'm pretty sure everybody wants to get an egg in the class.
Well, desire and
We're all here.
compensation for well-admitted effort are two different things, right?
We're all here. We're all putting forward.
That wouldn't be like
Where's your
3
I got
something, would it?
2.81.
2.81. I don't believe you. Did you forget to square this bottom part, the 1, 7?
Oh, yes, I did.
I got 0.3 something.
Point?
Yeah, that's all right, right?
Okay, that's all right. I would have figured by, after a semester, you guys would have had this calculator thing down at this point. I'm guessing not. Let's see. Okay, so 1, 3, 1, 7, 3, 1, 10 power 3. wait. Was the moon? The moon was 22 or 21? 23. 22, right?
It says the 23rd.
Yeah, but it's actually 20. It's a typo. It's 22. So it's 1.62. Right?
Yes.
Okay, so you'll notice now that there's a slight difference, right, in the two. But in reality, it's not that big a difference. So you could literally figure out where you are. You know, when you get abducted by aliens, you know, bring a string and a little anything to tie it to, and you can figure out, you know, the acceleration and gravity on it. From there, you figure out what planet you're on or near.
So just to be clear, on the second to bottom line before the 1.62, it's 6.671 times 7.34 over the
This one?
1.7.
Yeah. So instead, it's going to be minus 2 because it's 23, not 22.
Okay, so it's all that parentheses basically, and then 10 minus 2.
Yeah, it's just times 10 to the minus 2. Yeah.
I'm just making sure there's not
Yeah, you're good.
small numbers.
No, but you should actually be putting it like this in your calculator. I was just trying to see if I could clean it up for you a little bit. I mean, because sometimes I get tired and sometimes I'll start messing this up. So all it asks for is what is it? Compare it to the one on the moon, the theoretical one, and then was there anything else, or just compare the two?
Are they the same in
Okay. Explain. So what are we going to explain? Why are they different? Why might they be different? What could possibly be wrong? Was Newton wrong? Is something broken? His head was broken, but he did some really good work. So the thing is, there's a difference. Now, do you guys remember when I talked to you guys about the pendulum in the first place? What did we say? We said something about it. We said something about it. Yeah, part of it's related to the equator. What else? I mean, what about the equator made it special?
Something about the actual effective gravity.
It's different from the equator to the pole. And it's because of what? Because remember? Because the Earth is rotating. Remember the Coriolis force? So in reality, we don't know where we measured it. We didn't say we did it at the equator on the moon. It could be anywhere. Now, ideally, if we were at the equator, we should have gotten exactly the same number because there's no Coriolis force there acting on it. So, because the rotation of the moon, we're having a difference in the local acceleration of gravity because of the centrifugal force acting on the pendulum. Got it? One more time. Say it one more time. Say what one more time?
Because of the rotation of the moon. Keep going. What's after that?
Okay, you guys are just going to spit it back at me without any understanding. That's what always upsets me, you know? Okay, because the moon is rotating, right? It's causing a Coriolis force on the pendulum, which is changing the local acceleration of gravity. How about that? Does that work? We're close enough?
Is causing a Coriolis force on pendulum. What else?
What?
What? What's after pendulum?
Okay. Okay. We're talking about this problem is about a pendulum, right? And the pendulum is oscillating back and forth at some frequency. Yeah? Now, what could cause this frequency to slightly change is because locally it's not only gravity acting on it, but also the Coriolis force because of the rotation of the moon. I've said it like 4 different ways there. The one that makes sense to you that you can explain in your own words. I said the same thing 4 times, I just said it differently. You're not slow. You're not slow.
Well, it takes me time.
Okay? So I'll keep number 3 for sure. I'll keep number 3. It's long enough for a final exam question, but these two are a little bit too easy, I think.
The number 3 is good. I like that.
Yeah, I think number 3 is fine, yeah. I'll keep number 3.
We cannot repick the last quiz. I mean, Sam. So please don't make it hard.
Please don't make it hard because you can't retake it. See, there's something fundamentally wrong with that attitude there.
I agree with that. We can't retake it.
But going into an exam with a knowledge that you can retake it is sort of fundamentally flawed. You understand that?
Without the knowledge, or with the knowledge that we can't retake it, that means we already do it as hard, and therefore it doesn't need to be harder.
Point. That should be enough.
Bill makes a point. There you go.
I think, yeah.
He finally speaks in class.
Vote for Bill.
Silver president, is that it? Okay, what's number 4?
A mass spring system oscillates with SHM. The path of the oscillation is recorded by a motion sensor, and the graph is shown in the following figure. Determine the amplitude of the oscillation in meters. Determine the period and frequency of the oscillation in seconds of hertz. If the mass is 5 kilograms, determine the elastic constant of the spring. Determine the maximum speed of the spring system and the location of maximum speed.
So you're given a plot that looks, I guess, something like that, right?
Right.
Okay. So what do we have to find again?
A lot of stuff. Determine the amplitude of the oscillation in
Okay,
meters.
we need the amplitude.
Period and frequency of the oscillation
Period.
in seconds and hertz.
Frequency. Okay.
And the elastic constant of the spring.
Okay. Okay.
And finally, the maximum speed of the spring system and the location of maximum spring.
Okay.
Maximum speed.
There you go. So that's what we got to find. Okay. So first thing is we know where does this plot start? It starts at 0 or it starts some
Zero.
0. So what do we know? If this is the position, right, and this is time, so what do we know? At t equals 0, what's its initial position? 0, right? This is 0, okay? No? You guys can't see that?
No, that is, yeah.
Okay, so we know its initial position. And what do we know about a spring system? We know that as it's crossing the 0 point, right? We know at this point it's all potential energy, right? And at this point it's all potential energy. Why? Because when it reaches this point, it stops moving for a second. So the total energy is all in the energy of the spring, right? And then as it comes to the middle point, the distance is 0. So there's no potential here. It's just kinetic energy, yeah? And then anywhere in between, say here, for example, it would be potential plus kinetic. You guys remember that? Okay, so in other words, the point at maximum speed is always going to be right here at the equilibrium point. Right? Okay, good. So that means Vmax is going to be right here at this equilibrium point. Okay? We can see here at x equals 0, at t equals 0, x equals 0. So what do we say? We said the general formula, right, for the spring is A cosine of omega t plus B sine of omega t. That's what we said. Yeah? And we know a couple of things, right? We know that omega is equal to the square root of k over m. So once we find omega and we know the mass, we can then find k, right? So we just have to figure out what omega is going to be.
I don't know if any of these are on the formula sheet.
Okay, so on this thing, the maximum height here of x, what do we call this? What? You gonna turn it? Why don't you just like slide it back on the table there? You get a bigger scope. It's got a baby face.
My face.
Is that your face? I don't think so.
That's my face.
That is not your face.
It is. That was.
No, this baby face.
Oh, okay.
Unless you have, pictures of yourself in diapers as the screensaver in your computer.
I think my family was too poor for that.
Your family was too poor to have you in diapers?
It has me in pictures. In diapers.
Pictures and diapers. So I'm not sure what went. The pictures of the diapers, but we'll skip that for now. Okay, so at this point here, what's this maximum distance here is called? What's this called? It's D max, right? So this would be D max, but it's also called something else. It's called the amplitude, right? So what is that highest point on this?
3 on the
3 on the graph?
Yeah.
Okay, so we know D max, or the amplitude, right? D max, which equals the amplitude, is equal to 3. And I think it's in centimeters. I don't know. I don't remember.
it doesn't say.
Okay, so 3 units, whatever. Okay, so we know the amplitude is 3, right? Now, in this time, does it give you the time in seconds or whatever?
Yeah.
Okay, so how long from this point to this point? 14
From where to where?
It's like
from
a
here
little over 10.
to there. So it's, yeah, it's like almost like 10 and a half or something, right?
Yeah, like 10 and a half.
Yeah.
Okay, call it 10 and a half. Okay, so that time from here to here, or we call that the period. Remember? Okay, so that means that the period in this case is going to be 10 point whatever 5 seconds, right? Okay. So we know the period. So we know a lot of stuff, right? If we know the period, what do we know? We know the frequency, don't we? The frequency equals 1 over the period, right? And we also know, right, the omega. Omega then is going to be 2 pi over the period. So now we know this frequency and know omega. Right? You guys are going to have to put calculators on to figure it out. But if we know omega, then we can solve this for k. So that means that k then is equal to omega squared times m. Yeah? Which is the 2 pi over t squared times m, which equals whatever. So now you found the spring constant. We found the spring constant. We found omega. We found f. We found t. We found the amplitude. This looks like a really hard problem. Okay, and then Vmax, you can do it a bunch of different ways. But Vmax, we know that this is the kinetic energy and this is the potential energy. So if you guys remember, the potential energy of a spring was the minus 1/2 k and then whatever, delta x squared. You guys remember that? This was the potential energy of a spring. Okay, at some displacement. So this is amplitude, whatever. So we know if the total energy is conserved, the energy here has to equal the energy there. So that means that the total energy at this point, I'll call it point A, right? It's going to equal the total energy at this point, I'll call it point B. Or whatever you guys want to call it, okay? So we know now K, so that means we know 1/2 times this k, and this distance from here to there is exactly our amplitude, right? Yeah? Did you see your last?
Yeah.
Where did I lose it?
You lost me at k equals blah, 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 blah. And then all of a sudden you started talking about total energy and everything like that.
We said here, the formula given to you is omega equals k over m, right? Square root k over. So if omega equals the square root of k over m, I square both sides, right? That becomes omega squared equals k over m, right? And now I multiply on both sides, right? This becomes omega squared times m equals k, which is what I wrote down there.
But then you started talking about something about total energy and stuff like that, and I got lost.
Okay. So anyways, you have k now. K is m times omega squared. You're going to write the number down. Whatever this omega is and this m is. Write the number down. Now we needed k because for me to compare the Vmax, I have to know A, where it is. Well, we know that maximum speed is going to be here. And B, what its value is going to be. Well, to know its value means we have to know its potential energy. So if we know the potential energy and we know at this point it's all kinetic and the total energy here has to equal total energy there. So the total energy at, I'll call it A equals the total energy at B, or whatever you guys want to call it. The bottom, the middle, equilibrium position, whatever you guys want to call it. So this is going to be the 1/2 k, and this distance is our d max or our amplitude. Okay? Squared. And then the total energy here is going to be just kinetic, which is the 1/2 m and then v max squared. Okay? So if you look at this real quickly, you can get rid of the halves, and what I can do is I can divide by m on both sides. Okay? Right? So that means my v max squared is going to be equal to k over m times amplitude squared. Wait a second. Isn't k over m omega squared? So that means that my v max squared is equal to omega squared amplitude squared. So that means my v max in general is going to be omega times my amplitude. That's your general answer, right? In this case, we have omega over here, whatever this omega is, this number, times the amplitude. When the amplitude you said was 3, right? So then you can have omega times 3, whatever omega is times 3. Whatever omega, and whatever this number ended up being, I don't know what you guys got for it.
So after looking at this, you really should keep 1 and 2 the same. Yeah, no.
This is a final exam, right?
I'm gone again, like at the exact same spot. I have no idea.
What do you mean exact same spot? At T, A equals TE? Is that where you're going? At this point right here?
Yeah.
Okay, you remember the total energy here is equal to total energy here. Do you remember why? Because there's no friction, right? So what kind of energy do we have right here? What kind of energy do we have right here? So if this equals that, that's all I wrote down. I wrote down here, this equals that. That's it. This equals that. That's it. Kinetic equals potential. Sorry, potential equals kinetic. What? Don't look at me like that. You just said you know what kind of energy it is.
I don't understand where you got all the formulas from.
Okay, you do know kinetic energy, right? Equals 1/2 mv squared. Remember that? Tell me you remember that.
Yeah, I do.
Okay,
It's just hard to like.
And
read
potential
what the
energy
letters, all
is-
the letters are from.
right there. Okay, so the point is that, as you said, we didn't need this one, so fine, we don't need it. Huh? Can you do it again? What do you mean?
Like start from the beginning.
No, it's all good. I mean, it doesn't make any sense. If you guys don't understand it, it doesn't make any sense for me to just make noise, right? Okay, so we have a plot that tells us that the oscillation is some sort of wave. This is the displacement, t. This is time. Okay? And I think right here is like 10. Okay, something like that. This is 0. Right? Something like that. Don't remember. And you guys said that on the picture, this guy here is like 3. Right? Kind of, sort of? Okay. So, what it's telling us we have to find, it's asking us to find what? It's asking us to find the frequency, the period, the amplitude. Of course, we want the angular frequency. And it's asking us also to find the maximum speed, right, of the spring, and where that happens. When do we have a maximum speed, right? So right from the picture, we can figure out a couple of things. We can figure out that this distance right here, which is our d max, okay, is also called our amplitude, right? So we know that our amplitude here is equal to 3. And let's just assume for now they're centimeters, okay? So I don't think they mean 3 meters. How heavy was the mass? Kilograms? Okay. 3 something, anyways. 3 centimeters, we have a really high spring constant. Okay, that's the amplitude. So we found the amplitude, done. Okay? Next thing, we look at the period. So the time it takes for this guy to leave this point, oscillate through, and come back to the same point and be going the same direction is here. So this is, we're going to call this time, right, which is the call the period, is 10 point whatever, 0.5 seconds. Okay? That's how we figured out the time, 10.5 seconds. We just found the period. So the definition is that the frequency equals 1 over the period. So does anybody know what that is? 0.095 hertz. Okay? Really low frequency. We also know the definition, right? That the frequency equals 1 over 2 pi times omega. Right? So that means that omega equals 2 pi times the frequency. Right? Which is 2 pi times 0.095. So whatever that is. Like 0.54 or something. Jennifer, if I lose you, you gotta tell me where I'm losing you. No?
I got like 0.5969.
Okay, this is rads per second, okay? So now we found the frequency and we found omega. We also have to find the spring constant. Okay, so now we also learned that omega equals the square root of k over m. That's the definition, right? So we do the manipulation. This means that k equals omega squared times m. So k equals omega squared, which is this omega squared, right? Which is the 2 pi 0.095 squared times m, which was 5 kilograms, right? So what was that, 2.7? 2.9?
So we just squared what we got before and then times that by the math?
Yeah, you can do that. I mean, you may end up with rounding. The reason I put it back like this is because you may end up with rounding errors. That's all. But yeah, you can do it. You have rounding errors. If you cut this like 0.59 or 0.6, and then you put it in here and square it, you're gonna have a different number than if you just carried it through. But it's fine.
At 1.78.
5 times 0.5 is gonna be pretty close.
1.78.
Okay, because I'm not squaring it, right? 1.78 in this case. This is kilograms, right? This is going to be Newton per meter. Okay? Probably higher. Let me see. So there's our K. Done. So now we have to determine where the maximum velocity is and what that value is. Okay? So as we said before, at this point it's all potential, at this point it's all potential, and at this point it's all kinetic. And as it's oscillating through, it's coming through here, stopping, and then heading back up through, accelerating, decelerating, stopping, accelerating, decelerating, stopping. Okay? So it means the maximum speed is at that point, is at equilibrium position. So we know where it is. Maximum speed, Vmax, right? In this case, is going to be at the equilibrium position. Right? That's the first part. And the second part says, what's the value? The way we figure the value is if there's no loss in energy, the total energy here has to equal the total energy here. So the total energy here is potential energy, which is the 1/2 k times delta x squared, which is the amplitude squared, right? And that's going to equal the total energy here, which is the kinetic energy, the 1/2 mv max squared. So what we can do is we can solve this for Vmax, right? So we get rid of the halves. We divide through by m, so we have Vmax squared equals K over M times the amplitude squared. So right here we realize that omega equals square root of K over M. So K over M equals omega squared. So it means we have omega squared equals the amplitude squared. Okay? That's Vmax squared. So now we can take the square root of both sides. Okay? That means omega times amplitude. Now this is a general answer. Your maximum speed is your angular speed times your amplitude. And remember, when we were talking about a circular motion, it was your angular speed times your radius, right? Well, your amplitude acts like your radius in the spring system. Yeah?
Quick question, when you do K over there, do you change any like value? Because I got 0.178. Are you multiplying it like 10 or something?
You got point 178?
Yeah, because it's 2 pi times 0.095 squared and then times 0.5, right?
Well, did anyone else get point? Huh?
It's times 5, not times 5.
Yeah, it's times 5, not 0.5.
Oh, okay, because I saw 0.5. My bad.
It's a teacher's fault. Professor's fault. We love you. Thank you for doing all this for us.
So I just have to remember that when I'm deciding on the question 1 and 2, right? Okay, so that means that Vmax is equal to what? We got the 0.095 times 3. We're going to assume it's centimeters, right? So if it's 3 centimeters, then it's going to be 0.03 meters. So that's going to give us something in meters per second. Or centimeters per second, it's up to you guys. -4, 27, 28, 28.
0.00285.
Pretty cool. Or 1, 2, 3. Okay. Did it ask for anything else? Or is that it? Okay, good. I can go home. Yeah.
So what's the elastic constant of the spring? What's that?
That's the K. K is it? Yeah. Again, that's the definition, right?
Sure.
So omega is the square root of the elastic constant divided by the mass for a spring. And for a pendulum, it's a gravitational constant divided by the length. Those are going to come up with multiple choice questions too. So you were right. That break in Thanksgiving messed you guys up. Meter, right? Cool. Like you know, right? Okay, I can erase. Jaws.
So it's 0.095. I can't understand. It's 0.095 times 0.03, right?
Yeah.
So it's
Yes.
the answer is 0.0285, not 0.00.
No, I'm pretty sure it's 0.0 because there's 1, 2, 3. Basically, there's 4 decimal places. It gives you a 28.5. It's 20. Basically, this says 28.5 to the 10 to the minus 4.
Because it's 0.095 times 0.03.
Yeah.
Well, I only get it. Can you do it and calculate?
You know, it doesn't matter what I get here. What matters is that you understand how to do it. You understand that, right? Because I don't want you guys just regurgitating the same numbers back to me. And I can almost guarantee the numbers are going to change in the test, right? You just said that 3 times. I can erase?
Yep.
Okay. Tanya, are you just like stressing over this test or something? What's going on? You're not acting normal.
It's final week.
It's finals week. Is that what it is? Okay, want multiple choice? Okay, let's do it. Let's do it. Multiple choice number one.
A common source of wave motion is
Is A. No. That's not.
What was A?
A is vibrating object. The answer is a vibrating object.
Well, what's C?
Vibrating object.
So what's A?
A wave pattern.
Okay, I didn't hear the wave pattern. I just heard vibrating object. So I got confused for a second. Almost all sound comes from a vibrating source. Except for things like a clapping of your hand or explosions. Has anyone ever watched the woodpecker in slow-mo, a high-speed film? That's pretty crazy. I mean, how does he not have a headache?
yeah. What's in their brain not giving them a concussion?
Yeah, exactly. They have like this tissue that's almost like a fatty, big fatty tissue, which cradles their brain. And plus, the birds aren't that smart to begin with.
Like bulls or whatever. You ever see that?
Yeah.
There's one video too.
Rams as well.
Rams or something, they hit, they killed themselves.
Yeah.
Number 2 is like a transverse wave, a longitudinal wave has question mark.
Okay, so any wave has an amplitude, has a frequency, has a period, has a speed, right? Anything else?
Without create a wavelength.
Okay, a wavelength. Anything else? There's another one. So okay. So you guys know the answer?
All of them.
Answer is A, all of them. Is that what you said?
It has all of them.
Okay. It also has Sonko Fora Fantaharis.
Which of the following is not a transverse wave? Sound, light, radio, all, or none?
Okay. Sound in general is a longitudinal wave. Okay? Because the sound moves like this, remember? Light, radio waves, all of those, they're oscillating up and down as you're moving. Yeah. What? You're fine? Okay.
How many vibrations per second are associated with 101?
So it is A. See, it's sound. You cannot break sound.
Cannot break sound?
Which is not transverse.
Break? What does break have to do with?
Transverse. I don't know. Is it A?
Okay. Sound is a longitudinal wave, which means it's not a transverse wave.
So light, radio are transverse.
Light and radio are both electromagnetic waves, which are both transverse waves.
So if you were to change the question, how would you change it?
It's a good question.
Which of these is not longitudinal? So which of these are a transverse wave?
So light is a transverse and radio waves are transverse.
All electromagnetic waves are transverse, from cosmic rays all the way down to radio waves. Just don't change the question. You know, I guarantee you guys, if I change the numbers in the question, you guys all, I mean, if I leave the numbers the same, you guys get like 100% as a group. And if I change all the numbers, you guys all get like 60%. Which means what? Which means that more than 40% of you have no idea how to calculate the number. That's not a good proportion. Okay, what was number 4?
How many vibrations per second are associated with 101 megahertz radio wave?
Okay, so do you guys know 101 megahertz?
I think it's more than megas.
Yeah, it's just 1 million and one.
101 million.
Yeah, 101 million. Sorry about that.
It's more than 101 million.
It's not more than 101
So
million.
is 101 million exact?
I don't know. Does it say 101.55 or something?
It doesn't, but I want to make sure it's not more than 100.
What's your favorite radio station?
I don't listen to radio. Oh, I listen to Pandora radio. Or iHeart.
99.5? DC 99.5? I like that one too. It's good. So that DC 99.5 would be 99.5 megahertz. Okay? So your radio station you like is 99.5 megahertz. This is the actual frequency in hertz of your radio station. There's also 100.1, right? Which I like a lot. There's a bunch of those gay bebop ones, but
Oh my goodness.
okay, we're good? We're clear? And if I said, what's 101 kilohertz, right? You guys would say it's just 101,000, right? Okay.
I thought it was 101 million. That confused me.
Okay, you only like listen to half of what I say. You're going to have a lot of trouble with your son, you know that.
Why?
Because you only listen to half of what he's saying. And you're missing the important stuff. The qualifier. Why did you do this? You're missing the qualifier of why he did it.
He can't talk back to me.
Oh, I said I'm not talking back. You're going to ask him why he did it. I guarantee you'll be in a situation where you be, what the hell do you think you're doing? This is a guarantee. I mean, this is not a gray area. This is guaranteed. I mean, he's already telling you what to do, and he's only this big.
He's one.
Where are you going? You're not allowed to go. Where is your sister in the other class? Kimmy is taking the test right now, right? Kimmy is taking the calculus test right now, right? You're not sure? I'm teasing you. See you later. Good luck. Okay, what's number 5?
Radio waves travel at the speed of light, 300,000 kilometers a second. Pretty fast. The wavelength of a radio wave received at 100 megahertz is.
Okay, so we're asking for the wavelength, and we know a relationship between the frequency, right? The wavelength equals the speed. So what was the frequency? 100 megahertz?
Yeah.
That means the wavelength is equal to c over the frequency. So this is 300 million. 300. Basically, it's 3 times 10 to the 8, right? Divided by, what was the frequency?
100 megahertz.
Okay. What? Answer is 3. Yeah, well, you go add 2. Yes, you're very good. Okay, so a wavelength of a radio wave at 100 megahertz is 3 meters long.
I was reading in the book that speed has nothing to do with the wavelength. I know I read that straight out the book.
Okay, well, this relationship, you got to trust this relationship. Now,
Is it like
now the wavelength will change in a dispersive medium.
Wouldn't it, if the wavelength changes, wouldn't that just change the frequency itself?
No, it will change the speed based on this relationship. The frequency is the thing that doesn't change. The frequency, unless it's interacting with something, some other nonlinear material,
Right.
the frequency is fixed, but the wavelength can get longer or shorter based on the material it's passing through. So when you see a rainbow or you're looking through a prism, the frequency doesn't change from when you're sending it in to where it comes out. But what happens is that the wavelength slightly changes, its speed slightly changes
Right.
based on its reaction to the material. That's why it spreads.
So how did you get 3 times 10 to
Okay, well, read the numbers, the speed of sound, speed of light for me.
Honestly, that cut off on my.
300,000
Yeah.
300,000 what?
kilometers a second.
Okay, so how many is in it meters per second? Okay, 300,000, right? Times 10 to the 3. Because you want to convert it to meters, right? No? So 300,000. So this is 1, 2, 3, 4, 5, 6, 7, 8. There you go. Perfect. I can do it in both hands. I don't even need my thumbs.
Where did you get the 10 on the to the third power? I'm confused.
Okay, it says kilometers. It says 300,000 kilometers a second, right?
Yeah.
But if I'm going to do this kind of calculation, I need to do it in meters per second. So how do I convert a kilometer to a meter? Don't tell me you feel math. Okay, look, I'm going 10 kilometers, right? 10 kilometers. Kilometers. How many kilos in a meter? Kilo. Kilo means 1,000. Right, so this is equal to 1,000 meters, right? Times 10, right? Okay. 1 kilometer equals 10 to the 3 meters. Can you remember that? Which equals 10 to the 6 millimeters. No? 1 kilometer. Okay, forget a kilometer. 1 mile. How many feet in a mile?
A lot.
5,284? Huh?
Yeah.
I mean, what do you prefer, kilometers or miles? I'm just trying to figure out where the breakdown of this
I
is.
think kilometers.
Okay, well then kilometers. So a km is 1,000 m, right?
Okay.
If I said 1 million miles, this would be the 10 to the 6. Or 1 million meters would be a million. So the big M would be a million meters. Right?
So it's 3.0.
So no, I mean you could just keep all the zeros. I just didn't want to write all the zeros. I was trying to, but it is 8 zeros. Look, there's 8 zeros. See, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 zeros. So I can rewrite this as 3 times 10 to the 8 because there's 8 zeros. There's 8 decimal places. Got it? Okay. Okay, so that gives you a sense. Radio waves at 100 megahertz are 3 meters. Now you have radio waves that are thousands of kilometers long, by the way, in the universe. And those really long wavelengths are the ones that we actually see distant galaxies and stuff with, because they survive much better through space than these shorter ones do.
They're just like constantly growing, aren't they?
Growing?
Going on and on.
No. The wavelength. Okay, the wave continues along.
Yeah.
But the wavelength is just a measure from a point here until it returns to that point. So it may have multiple wavelengths in it, right? Like,
I'm thinking like water wave, like if you drop.
okay, so let's say I do this, right? If I do this, this right here, if this right here would be one wavelength, right?
Right.
And then I'd have another wavelength over here, this would be another wavelength, and so on. So even though the wave keeps on going and going, its wavelength is fixed. The time it returns to, that's a fixed distance. You get what I'm saying?
Yeah.
And the same thing with water waves. If you look at water waves, if you travel with the water wave, you'll see the distance to the next water wave is fixed.
Oh, you can see it if you watch it.
Yeah, you can see that they're fixed and they're just moving
I'm just
together.
thinking about how you drop it and they just keep growing up and up, like in a circle. Like,
Oh, you mean
Yeah,
like
that's
a ripple effect?
I'm just saying, they're just going out in space right now.
Yeah, that's
That's
true.
what it can be.
They just keep on spreading out in space, straight, until something absorbs them.
The frequency of a simple pendulum depends on its mass, its length, the acceleration due to gravity, all of these, or two of these.
Okay. The formula for the frequency of a pendulum is given to you as it depends only on gravity and the length of the pendulum. So then what would be the right answer? What were the options again?
It's mass, length, acceleration of gravity, all of these or two of these.
Two of these, yeah. Okay.
A sound source of high frequency emits a high speed, amplitude, pitch, all of these, none of these.
The speed of sound is not specifically frequency dependent, at least not in this range. So the speed of sound, I'll call it V sound, right? Doesn't care about the frequency so much. So it's not going to be the speed. So what are the other options?
Amplitude,
Amplitude has nothing to do with the speed.
pitch,
Well, maybe it does. We said that the speed is the frequency times the amplitude for a spring. But we're talking about the frequency, right?
yeah, high frequency emits a high.
Okay? What we're really talking about is high frequency. We're talking about the pitch. Higher frequency, higher pitch. Okay? So the correct answer is the pitch.
Double the frequency of sound, and you also double its wavelength, speed, amplitude, or all or none of these.
Okay, so if the speed of sound doesn't change, if you double this guy, what happens to the wavelength? If this is a fixed number, and this gets twice as big, but then this has to get half, exactly. So then the wavelength becomes 1/2 the other way. Right? Because the speed has to be fixed. What? What are the choices?
If you double the frequency, you double
You
it.
also double, but you're not doubling that.
Yeah, you can.
Okay.
So none of them.
But you can imagine a lot of different ways I could ask that question in the test, right?
But this one is none of these, right?
I don't know.
By saying sound. frequency of
Speed does
sound.
not change. We're saying that the wavelength has to go at half if the frequency doubles, or vice versa. If the frequency halves, then the wavelength has to double. If that isn't one of the choices, then it's none of the above.
Nothing happens to the amplitude.
No. Amplitude is not related to the frequency.
Sound travels faster in air, water, steel, vacuum, or it's the same at all.
So what did we say? We said that in a gas, it has a lot more room to move around before it hits the next guy, so it takes that much that delay for the collision to move the thing forward. In water, they're a little bit closer together, but they still can move in random directions. But in a solid, they can move in a straight line, and the atoms are very close together, so the energy can propagate through very quickly. So steel, being the solid in that, is going to have the highest speed.
The vacuum is irrelevant.
The vacuum is irrelevant because in a vacuum, sound cannot travel. Why? Remember I said in space they cannot hear you scream, right?
I was just answering.
So if there's no material, there's no way for the air or the sound wave to move the other material because of collision with the other material. Because it needs the material to do it. The difference is the electromagnetic wave or the transit waves don't require a medium. They themselves have their own energy. So they can travel through space and time without any material. Without any medium, as we call it. This we're talking about 1780, 1790 time frame where a bunch of really drunken scientists talked about the ether.
The natural frequency of an object depends on its size, shape, and elasticity, which is
So what we said was that its shape, the material it's made out of, which is related to its elasticity, right, and its size all contribute to the natural frequency.
The size does not.
It absolutely does matter. It doesn't matter what your girlfriend tells you.
I mean, I put D because in the book it just says shape and elasticity. So I was just like, I was sitting there looking. I'm like, I feel like this is not.
I'm sorry, Jennifer.
I'm too tired.
Red is so red.
Yeah, she is like beet red right here.
It's a good thing you can't tell if I'm red or not.
Just like it.
I don't turn red.
I bet you I can make you turn red. I bet you I can make. Listen, I'm not gonna go there right now, but
Are you gonna
let's just
tell
say,
them
you know
about
that song, about making women blush. Just let me put it there.
I think that's a dark blue blush.
Okay, we good?
Yes, the answer. Yeah. A was the answer to that.
So basically, all three of them.
The least energy required to produce forced vibration in an object occurs below its natural frequency, at its natural frequency, above its natural frequency.
The least amount of energy to cause a resonance is always going to be at its natural frequency.
This next one's about heat. I don't know if this was like a trick question you're throwing it in there, if it was a mistake.
I don't know. I think there's 15 questions in this test, right?
Yeah.
So probably that won't get dropped.
Yeah, this was from last week. Anyway,
It is.
Okay, let's go straight to 13 then.
okay. Caruso is said to have made a crystal chandelier shatter with his voice. This is a demonstration of an echo, refraction, beats, pretty awesome beats by the way, resonance or interference. Resonance.
So what was 11?
11 was at the natural frequency. And 12 was null.
Did you see the Mythbusters episode where they did the resonant frequency stuff? They put a thing on a bridge to make it match the frequency.
Ah, yeah.
So when you say
And it
no,
started
does that
to
equal
actually
0?
shake and they got really consistent.
Yeah. But I mean, Tesla almost took down a whole building like that.
Yeah, exactly.
From a little oscillator that was this big.
They made the same thing and did it on the bridge, and it was a public bridge used in California. I had to stop really quick.
And wait, they didn't actually get permission to do it beforehand or
Well, they
something?
did on the bridge, but they didn't think it would actually cause that much of a reaction. So they just really hurt this time.
So when you say no,
When I say no,
0, nada, nothing.
when I say no about what?
Question, well,
These things are tough.
What I'm saying is that in this example test, there's 15 questions. In your exam, there'll be 14 questions. So more than likely, the heat question will not be present during your final.
it's not a heat question.
It's not a heat question?
Yes, it is. Never mind. Okay. 13 was
all other things being the same, strings having more mass than other strings will produce a higher frequency, a lower frequency, or the same frequency.
Strings with what? Higher mass?
More mass.
Okay, so if you guys remember, you had n square root of mg over mu times 2l. I don't know if you guys remember that or not, but remember that? So that mu is the linear density or the mass of the string. So as this gets bigger, your frequency is going to do what?
Go lower.
Go lower, exactly.
Just like a basic tone.
So isn't that answer the question though?
lower frequency notes.
So imagine I can change that, right?
I don't think you could figure out a way to change it. That'd be complex.
No, just say.
Switch one word. Alright. Compared to a sound of 30 decibels, a sound of 60 decibels is twice as intense, 10 times as intense, 100 times as intense, 1,000 times the 10s, or
It's not 10.
10 to the 3 times the 10s.
Is it 30? 30 decibels?
Yeah, 30 decibels. The sound of 60 is what compared to
Like 30 tell.
Okay, so we have two sounds at an intensity at 60, intensity at 30. We want to compare them. The easiest way to do that is just take the ratio, right? So that's going to be the I0, 10 to the 60 over 10, divided by the I0, 10 to the 30 over 10. I0s have it, and this becomes 10 to the 6 minus 3, which equals 10 to the 3, which equals 1,000. So we're saying that the 60 decibel sound is 1,000 times bigger than the 30 decibel sound. That's what we're saying.
Yeah, crazy stuff.
Yeah, but you guys do understand that that's exactly the decimal. Your volume scale on the thing is a decimal scale.
Like 1 through 10?
So if you're at a 10, you're like at 100 times or maybe 500 times what you are at 1 or 0. You could measure it. And if you guys get something that's 3 dB, typically you say 3 dB bigger than something else is twice. A third, if you go 3 dB up or 3 dB down. It's actually 1.975, something like that. Maybe you should round it off to 2. So any questions? We're good? When Mahat does it, he usually holds it so he can see what he's recording. Just saying. I'm talking about the computer. And one of the videos you saw, he's the one who actually did the recording.
Oh, like this?
Well, he holds his computer. He has but he uses a tablet.
I won't know. My tablet is.
So hey, that's pretty good. Even with the delays and the rooms and everything else, we still got it done in an hour and 45 minutes. It's not bad. You have a question? Yeah, mu is the linear density. It's the linear density, right? This is mg is intensity, and then mu, in the case we had mu equals 4.4. Remember this? It was 4.4 grams per meter, something like that, right?
So his mass is like there.
Yeah, so grams per meter. So this is the linear density. So as you increase the weight of the string, then this number goes up. Right? Well, this is the mass. This is the tension. This is the tension.